Astronomers, morning has broken. Shokin farewell. parts of astronomy.
Oh, thank you, Kim. That was really lovely. Thank you so much.
Thank you
Again,
for having me.
as usual. We're so glad you're still willing to share your music with us. It really makes the...
I'm so glad you're willing to allow me to be here. Thank you.
Yeah, well, I think it's time for us to actually formally start the meeting. Is it changed over, Reza? Okay, welcome everybody to the July meeting of Orange County Astronomers. We're really glad you're all here. And we hope that you're having a better summer than last summer. At this time, unfortunately, we still do have to deal with a certain amount of COVID considerations. Before I turn it over to our announcement crew, maybe I should introduce myself. I'm Barbara Toy, in case you've forgotten or don't happen to know who the current president of the club is. You'll be hearing from our vice president and others later. Before I turn it over to the announcement crew, I've been receiving a few questions from people by email on what we're doing about various events. And one big question that a couple of people have asked is, are we doing a Starbecue this year? The answer is, unfortunately, we've decided, we being the board, that it's just still not a good idea to have that kind of gathering. And so we're going to postpone that till next year. But we're hoping we're going to have a really big party next year. So look forward to that, plan what you're going to bring. And we'll see you all at ANZA July 2022, probably. The other, another question was whether we're going to start formal star parties. We are limited on Orange County star parties to what Orange County Parks will allow us to do. So far, they have not allowed us to restart group meetings such as our star party would be. As soon as we do get the go ahead for that, we will post notice on the website and send it out on the email groups. So please keep your eye on that. And if you have questions, you can always ask anybody. Actually, you should probably direct it to me, to Alan, our secretary, or to Charlie. Charlie is the one that tends to be in contact with the county people because they always want to know about our insurance. The last item is meetings at Chapman. We will presumably at some point go back to having some form of in-person meeting, but that will only be when Chapman allows us back in. And the earliest they have told us that's likely to be is September. It may be after that. They are supposed to contact us near the end of August about what their firmer plans are going to be and to set up a schedule at that time. So, hang in there. When we know, we will let you guys know. And in the meantime, we're still trying to figure out how we're going to keep the benefits of this remote arrangement along with the benefits of in-person arrangements as well. So with that, I will turn that over to our announcement crew. Kyle is unfortunately not able to be with us this month. So the announcements will be Cecilia Caballero, Paloma, Galileo, Helen Mahoney will be assisting, as well as Alan Smallbone. So take it away, guys.
All right, welcome to today's meeting, everyone. New members are coming up soon. Thank you for coming. Okay. So the next board meeting is this month, July, online to be announced. The beginning is August 6th, also online. Barb will start. So each events, it's already a new year academically, and we have been getting so many requests for August, September, and we've been saying almost. At this point, we're going to start some of them already at August, September timeframe. So I'm going to email all the volunteers that you guys feel comfortable doing live events and are already fully vaccinated. Also, we're waiting to see what schools are saying about how they're going to be handling the distancing from now on. But yeah, we have, looks like our first event will be booked for November, October timeframe. So we're looking forward to that, going back on ground.
Again, sadly, my brother Galileo cannot attend this meeting. Obviously, today is a new moon.
We have the Serious Astronomer, which all of you know. We get that as a monthly either PDF or mailed to you. Dave Fisher, who is the volunteer editor of the Serious Astronomer, is always looking for articles or items of interest or images or anything you have to say that's astronomy related, or if you have equipment for sale, please contact Dave Fisher. His contact information is on the website.
Hello. There is going to be an article in next month's Serious Astronomer, and it will probably be on our website later this month. We have been sending out most of the Serious Astronomer newsletters by hand mail, and we can save money for the club and save a tree because we can do this on the internet. So we'll have some information. If you are interested in not getting a paper copy, we'll have some ways on the announcements for you to know how to get that information to Charlie, who's our treasurer and who is very good at putting this out every month. So with Dave Fisher's help making the Serious Astronomer and Charlie getting it distributed, we all get this every month, and we're just trying to make it a little bit easier. So look for that in the website and in the Serious Astronomer in August, and we'll let you know how you can help out with that. And talking about opening things up, yay! Owens Valley Radio Observatory is opening up this month, and they have allowed us to be their first outreach in the post-pandemic era. So we have been doing this, Doug and Cecilia have been doing this for over 15 years with Mark Hodges, Dr. Mark Hodges, who is our connection there. And if you've never been to OVRO, this would be a good time to start. We have a wonderful program there. We do science, we do experiments with liquid nitrogen, and we get a tour of the great big 140 meter dish. And it's a wonderful time. And then we also do a star party because it's very, very dark. As you can see in the picture there, that's what it looks like. You can see the Milky Way and other beautiful things that are up this month. And so if you are interested in going, the contact number is down there. It's also on the back of the Serious Astronomer because Doug's one of our board members. So it's Dr. Zarkov56@yahoo.com. Email him and let him know you'd like to go, and he'll send you all the information. Hope to see you there.
The ANZA site, we're still discouraging visitors until further notice, and we'll send out a notice when star parties will start. And we're also saying no members at this time, no guests. And it's not really possible for us to maintain a sanitized environment at the house. So please follow any things that you need. Bring your own sanitation gear. And of course, as always, pack out your own trash, please. And we need to clean weeds, even though we haven't had that much rain so far. We've had some monsoon rain, and the weeds will start growing. We're trying to cut some of them back in the public areas, but any help that you can do, and especially if you have a pad or an observatory, it is mandatory that you clean up your own area. So please do that and haul off any cuttings that you have. Either bring them to your own trash or take them to the transfer station in ANZA. And the next meeting is August 13th, which will be online. And tonight's presentation, the What's Up, is by Dr. Doug Millar, and our featured speaker is Dr. Armin Rust. Doug?
There, can you hear me and see me now? Nothing.
Yes, we can all hear it, see you. Thank you, Doc. Please
Okay, good.
proceed.
Okay, so what's up, Doc? Only makes sense. This What's Up's going to be a little bit different. We'll talk about observing at H1 or neutral hydrogen frequencies with a radio telescope and a mobile observatory app and what's up. So neutral hydrogen is when the hydrogen electron gets banged by something, it flips and emits energy at 1400 megahertz, 1420.407 megahertz, which is pretty low radio-wise, and it's pretty loud. But the things that do it are pretty big, so it makes it fairly easy to observe anything like that on radio frequencies. What you're likely to see is Cygnus A or Cas A, or the Milky Way and particular arms of the Milky Way. So it has some interest, and it's easily done in terms of radio astronomy. And it's possible with modest equipment. Best of all, you can do it in the daytime. So here's what I did when I made my own receiver to try and do that. I used a 6-foot umbrella dish with a 1400 megahertz feed and a homemade down converter, and a back end that didn't work. I'll tell you more about that later. Here's the dish. It's pretty cute. It takes a relatively small tripod, and it folds up and stashes away easily. Unfortunately, it blows down pretty easily if you don't weight it, and we discovered that. But it's a 6-foot dish and has good gain at 1400 megahertz. And the quickset tripod allows it to be pointed pretty much anywhere in the sky where you think there's something to look at. Here's the receiver. The green box is a signal generator at 1400 megahertz. The black box is holding up the blue box. And then off to the right is a mixer, a Watkins-Johnson 4 gigahertz mixer. And the black box on the bottom is input to the preamplifier and filter. And the output goes through a bandpass filter at 20 megahertz for basically a high-frequency receiver. And that system all worked. We were able to verify with some noise that was a functioning system, but we didn't know enough at that point to really make a good back-end circuit for it. And we found, in case anybody's interested in doing this, that using an RF space SDRIQ receiver, it's a direct sampling receiver at 20 megahertz, and then setting the averages up to 125 should give you some signals. And they're pretty loud, really. The preamp is about 0.8 dB noise figure and 40 dB gain, has a filter in it. So the Haystack Observatory has a similar radio, and this is what they got with the SDRIQ SpectraView software. So you can see they received something, and I'll let you know how you know that in another couple of slides. So in the meantime, fooling around on the internet, we found that there was a remote H1 or neutral hydrogen observatory. They would give you free time, and all you had to do was put in your email, so that after your observation they would send you the observation. The only limitation is that it's a zenith transit telescopes, and that's better shown than explained. The guy got an old microwave dish and lined it with chicken wire and put a feed in the middle of it and just points it straight up, and whatever goes over in the sky is what he picks up. Fortunately, there's lots of things that go over. And it works pretty well. Hooked up on the internet, has a good back-end software, and the name of the observatory is Pictor Observatory. It's a free remote observatory. It only receives a neutral hydrogen. It's in a transit mount that only sees straight up, and it emails you when you're done. The only other thing you need is a Planetarium Program. And I'll mention that in a minute. Here's the data I got back after a 2-minute observation. Here's the raw data. Here's a different presentation of it. Here's the calibrated data. And this is one of the arms of the Milky Way. So I actually received something first time out. So there's a YouTube on the Pictor Observatory. You can just do a search on Pictor Observatory, and up will come the YouTube video, and it'll tell you all about it. But you need a Planetarium Program. Meade makes a program for free that you can download for their LX200 telescopes and other telescopes. That's a big movable sky map. So what you do is you set the Planetarium Program and tell them you're located in Athens, Greece. And then you change the time to the current time in Athens. Otherwise, this won't work. and you use a zenith projection. So it lays the sky over that location with all the objects in it. And you can see what the telescope's going to see in the next whatever period of time you want. The dish has makes about a 10-degree hole in the sky. It'll see anything within 10 degrees of straight up. So it isn't just a single point. It's actually fairly broad. So the resolution is very raw, but you can differentiate different arms of the Milky Way and certain objects. So with the projection, the Planetarium Program, you can go back to the Pictor Observatory, and you know that one of the arms of the Milky Way is laying straight over Athens. So you do a 2-minute observation and hopefully get data like that. Very simple to use and free, I might say. Quite a nice setup. There are other observatories that do that, but they don't give away free time. And it's an alternative to building your own stuff. So I would say start with a Pictor site and get excited about that. And if you want to get more advanced, you can build your own receiver. And of course, if you want to get more technical details on that, give me a call or message me or email me. So here's the second part of the What's Up talk, and it's about the Mobile Observatory. And I don't know if you've seen this before, but it's an app that you can download from Google Store and other places for your phone. It's an inexpensive planetarium program and real-time viewer. There's a simple level, which I found to be completely adequate, but there's a pro version. There's always a pro version of everything. I think it's a lot better, but it's $9. You know, if you think of how easily money goes through our fingers as astronomers, this is not bad money. It's from Google App Store and other places, and to say that the thing is a comprehensive program is an understatement. Here's some ideas. This is the main menu. There's a sky view, okay. There's a live view, and what you do is you take your phone with the program going and put it in front of the object you're curious about up in the sky. And on the phone, you see that object and an explanation of it in real time and all of its friends. Oops, that's not going to work. I should hold on to the phone better. You can squinch it together or spread it out and go way into 10th or 12th magnitude. So you can stick your phone up anywhere in the sky and see what's there for a live view. Anywhere. Doesn't matter what the light pollution is, you're going to see what's up there. So like if you see a bright object in the sky, you're not sure what it is, you stick it up there and it says, oh, that's Jupiter. Okay, but that's a simple version. But you can do almost anything. All right, there's still 24 more things you can do. There's tonight's best. It gives you a list of, from the brightest to the least bright, of all the good stuff that's up tonight. Solar eclipses, that's nice. Sun and the moon, it just goes on and on. Where the Galilean moons are supposed to be, where the Saturnian moons are supposed to be, everything in the palm of your hand. Oh, and here's what's up in the sky the particular night that I took the picture, and it's in Spanish, because you can set the program to do Spanish. Won't do Chinese, won't do Japanese, but it'll do Spanish. So this particular night, of course, the sun is the brightest. And then the moon and Mercury, Venus, and this is their rising times, transit times, and setting times, and they're I think they're magnitudes. Jupiter, Saturn, and then it goes down into deep sky objects, and it just keeps going, and pretty much in order of brightness. And then here's tonight's best stuff in order of brightness or best visibility and the time. So if you want to know what's up, then get out your program, hit the tonight's best, and see what's up, and then tell it you want to go see that, and put your phone pointed up, and it will show you where the object is. Like if you want to go to the Andromeda Galaxy, you put Andromeda Galaxy, link it, and the phone will say it's that way. So you go turn around a little bit. Okay, keep going, and it'll point up, and you go up, and then it'll make a little bingo sign when you're pointed directly at it. That's pretty cool. There are things that people have done lately with telescopes. They will point a telescope that way as well, but that's a subject for another night. So here's that same live view, and here's Jupiter was the target. There's the bingo mark. Here's the information about Jupiter, and then here's some tools that you can use to mess around with the image. And up here on top, of course, is the regular kind of tools like moving around and projections and so forth. So this is really a very extensive application. Helen and I were helping out our sister astronomy club at the Delray Yacht Club, and one night I showed them this thing. There were about 20 people. They all downloaded it, which I'm sure you're doing now. It's downloading this program, and we had a whole class on the program. It's not difficult. You're going to want to wander around in it and do all kinds of stuff with it. Okay, so get the Mobile Observatory. Download it now, so you can go through the rest of the what's up and know where stuff is. Okay. All right. Now for what's up, Doc? I've been waiting years. I have been waiting years to be able to say that. Okay, tonight's list of objects to see. Thanks to Helen and her built-in ephemeral catalog in her wonderful brain, she knows that Venus and Mars will be next to each other and the crescent moon on Monday night. Yahoo. Tuesday, Venus and Mars will be half a degree apart. That's pretty cool. So, but this time of year in July, you're really amiss if you don't go some way where it's dark and enjoy the Milky Way. So start at I always start at the bottom because the bottom disappears first. Start at the bottom and work your way up. M6 and 7 are not to be missed. They're great in binoculars. They're great in a telescope, and there's nothing else like them with the same sense of presence in the sky. I mean, they're globular clusters or clusters, but they're to me they're very special. And then M4 up in Scorpius is just pleasant to look at. M28 and 29 in the teapot, moving over to the left, more clusters, and then go up to the nebulosities, M8, M20, 17, and 16. So you're moving up the Milky Way from the south to north. And then you can. There's some things to look at, M objects and whatnot. I mean, this whole Milky Way journey is got hundreds of items, but at least you want to see these. And for me, every time I get a chance, I look up at the Milky Way and I see these things. I've seen them dozens of times, but they're old friends. They're just old friends. Like Albireo, I like to go to the Hollywood Bowl with a pair of 50mm binoculars and look at Albireo straight up. People don't know what I'm doing. They think I'm nuts, but they aren't the only ones. Albireo is Beta Cygni. I think that's the right way to say it. And then in that area is M27, 57, and 29, all worth looking at, nebulosities, and very pretty, really. The bigger aperture you can use and the more magnification they'll stand, the prettier they look. And then the last one I'll mention is the Veil Nebula, and there's at least two sides to it. In most good-sized telescopes, in fact, even my 100mm binoculars with a nebula filter can see the whole thing. You sort of see both sides of it, and there are other things to look at. So spend some time observing it. Get a map of the Veil Nebula, which you can print out off of the internet, and look for the little blotches and things that you normally wouldn't pay much attention to. A lot of it's there. So by that time, your Saturn and Jupiter will be up because they're going to come up late after midnight until, I think, when we go over to OVRO, they'll come up about midnight, maybe midnight, 12:30. So that would be a good way to cap off your observing night is with Saturn and Jupiter. So that should give you a fun night's observing. Well, Doc, that's the what's up. Thanks for watching. Here's some resources. This will be posted on our webpage, and this is the YouTube as well as the project. Again, if you would like to contact me about the electronics, please do so. Okay, Reza, that's it. Thank you.
Thank you very much, Doc. That was a WhatsApp presentation for all time. You taught us fishing and how to go and figure out what's up every night. Thanks. There's a couple of questions. So let me remind everybody the name of the app that Doug introduced us is Mobile Observatory. And that's available on Google Play Store. I checked iPhone and there's something similar called AS Guide. And there are a couple of other astronomy related apps like Sky Guide, Night Sky, Sky Safari, Star Walk, for those of you who are interested to have to know what's up at the moment on your phone, on your location. And also, let me remind everybody of another cool project that Doug introduced, the Pictor Observatory. Basically, it's a radio observatory freely available to you. You could go to their website and order images. Okay, with this, let's start the second session by introducing myself. My name is Reza. I'm the Vice President of the club. I, too, would like to welcome you to the July 9th, 2021 General Meeting. Before introducing our speaker of the night, I should emphasize that the goal of our meeting is to promote astronomy to everyone, and hence we encourage you all to ask your questions without any inhibition. However, in order to keep the quality of our meeting, we do not handle questions verbatim. We combine, rephrase, and reorder them to fit the natural flow of the talk. Thus, to get your answer, listen for the concept to ask about rather than your name or your words. Please feel free to use the Q&A button on your Zoom client to ask questions during and after the talk. You can also use the chat section to send us any comments you may have. Our speaker at this meeting is an associate astronomer at Space Telescope Science Institute. Originally from Germany, he came to the US as an exchange student and decided to stay to obtain his PhD at the University of Washington. After his PhD, he worked as an NOAO Goldberg Fellow at the CTIO Observatory in Chile before doing another postdoc at Harvard University. He started to work at STSCI in 2010 and has been working there since as an NIR James Webb Space Telescope instrument scientist. His research interest is focused on supernovae, exotic transients, cosmology, and gravitational waves. Please join me by clapping your hands virtually in welcoming Dr. Armin Rest. Dr. Rest. Oh, I need to unmute you, I guess. Yes, here it goes.
Sorry. Thank you for inviting me. It's a pleasure to be here virtually. It would be so nice to do this again in person. It seems like a lifetime ago when I gave my last talk in person, and that was just 1.5 years ago, just before the pandemic started. But it looks like it's getting better now, and hopefully we can do these things soon in person. So my talk today is about how we chase supernova with a Kepler telescope. It is a really great example how you can do really great science piggybacking on a mission that has a completely different science goal. So first I want to talk a little bit about the astronomer and the mission. Johannes Kepler, he was a true giant in his time. He was a mathematician and astronomer. He was an assistant to Tycho Brahe and a contemporary to Galileo, to other absolutely fantastic scientists, of course. He improved on Galileo's telescope design, which allowed him to measure angular distances between stellar objects very, very accurately. And at that time, that was like immensely important to do these first calculations about the motions of the planets and where the stars are. So these observations by Kepler allowed him then to determine the laws of planetary motion that still have his name. And they were also the basis of Newton's laws of the universal gravitation. So it was a truly amazing time where just a few people could do so much progress in science. And last but not least, Kepler also discovered the supernova in 1606, which is now called Kepler Supernova. This supernova was the last supernova that was visual, was observable from Earth in our galaxy. So it was, you could see it in the daytime. And there was another one just a few decades before discovered by Tycho Brahe. So they had like 2 supernova within 50 years. And we have been waiting more than 400 years now to see the next one. So the Kepler mission is named after Johannes Kepler, and it's a NASA flagship exoplanet mission that has been going from 2009 to 2018. It's a truly amazing telescope and instrument. In one image, it can image 100 square degrees. You just have to imagine that. It's a really big area. And most importantly, it has exquisite light curves. So it can follow up stars and other objects with a cadence of just 1 minute for really bright objects and 30 minutes for fainter objects. And so every 30 minutes, it takes an image, and you can measure the flux, and you can measure variations that are 10 to 100 parts per million. Normally, when we have a ground-based telescope, we are pretty happy if we get a 1% measurement, and extremely happy if we get like, 0.5% or 0.2%, but nothing even close to what the Kepler telescope, has been producing. One of the downsides is that it only downloads selected pixels from this 100 square degree. And the reason is just technical. It just takes time and resources to download all of this data from the spacecraft to Earth. And so unfortunately, they could not download all of these images. That was really fine for the main mission of looking for exoplanets, but for other things, like things that I'm interested in, like supernovae, it would have been so much better if they would have downloaded the full images. I mean, we could have done so much more science, but you take what you can get. So the Kepler telescope works like this. On the left side, on the upper side, you see a star with a planet that orbits around the star. If the inclination of the orbit is just the right way, at some point, the planet moves in front of the star. And that just leads, so it obscures a little bit of light from the star. The planet obscures the light from the star. And so when you monitor the star, you can see this little dip in brightness. And that's what the scientists that look for exoplanets are using to find all of these exoplanets. So on the lower right side, you see the focal plane, the area that Kepler covered, and it shows all Kepler transits of planets within 1 week. The size of the circles gives you the size of the planets. So these big circles are like Jupiter, and the really small ones are like Earth. And the color gives you how hot it is. And everything red is like lava. It's even hotter than the surface of Venus, which is kind of like yellow in these plots. So as you can see, the vast majority of these planets are just like really hot and really big. And the reason for that is that you have an observational bias to detect these big these big objects very close to the star. And that's the reason they are so hot. Because this obscuration, this occultation of the star is most likely when you have a planet really close to the star, because first of all, it orbits much faster around the star, so you have many more of these transits. And furthermore, you have this obscuration of the stellar light with many more angles than when the planet is very far away. So with this method, this transit method, you mainly find these very big planets very close to the star. And you can see this even better in this plot. So this plot shows all these planetary systems that Kepler found in his first couple of years. And if you look at my cursor, the solar system, just the inner planets, you can see here. And you can see that just the inner solar system, just like the terrestrial planets, are much bigger than the vast majority of the planetary systems. And if you look at the outer planets, you know, we don't have any system that are that have planets as far away as Jupiter and Saturn and any of the other gas planets. So I think Kepler, with respect to exoplanets, was just one of these absolute fantastic successes. I still remember when they had the first press release and the first batch of planets, and it was like, wow, you're going from like, you know, a couple of dozens of planets that we know to thousands of planets. It really has been a complete game changer. So I was in Maryland, the University of Maryland, gave a colloquium about something different, about light echoes of supernovae. And after my talk, a researcher at the University of Maryland comes to me and he says like, yeah, hey, Armin, do you want to see something cool? So I've never seen him, met him before. And I was like, sure. And so he opens up his laptop and shows me this plot here. And my jaw dropped. I was like, absolutely, you know, I mean, I immediately saw this is like a transient. I looked at the time scale. I was like, wow, this looks like a supernovae. And, you know, I've never seen a supernova light curve with such a beautiful cadence, with so many data points. And so the interesting part was that friends of mine, colleagues of mine, they had a project with Kepler and a program, and they wanted to find supernovae, and they observed 100 galaxies, and they didn't find any. And Rob and his colleagues, they were looking for AGN variability, and their program had 400 galaxies. And they had, it turned out they found 6 supernova in these 400. So my friends who had 100 just like got completely lucked out, because, you know, if you look at the statistics, they should have expected, they could have expected to find like 1.5 supernovae, and they found none, you know. So that was just like bad luck. And one of the colleagues of Rob at Shire, he was like the one who did the reductions. You know, he remembers when he looked at this and was like, what's going on here? I mean, that's something is wrong. And you know, in science, the most of the discoveries are like, this seems really wrong, and not like, oh wow, look at this, you know. So I brought then these two groups together, the University of Maryland people and my other friends. And so this was kind of like the seed for the Kepler extragalactic survey. And we started to, you know, look for supernovae, for more supernova in the Kepler data set. So before I go on, you know, just like a quick introduction to what are supernovae. The stars go through a life cycle, and there are basically 2 different life cycles. One of the relatively, or like the very massive stars, and then the other one with low mass stars. And so let's look first at these low mass stars. So if you have a star like the Sun, you have in the core fusion from hydrogen to helium, and that fusion just produces enough energy to counter the gravitation that wants to press this gas cloud together. And so, you know, our Sun has already lived for 5 billion years, and it will happily burn more hydrogen to helium for the next 5 billion years. But then at some point, after this long time, it runs out of hydrogen in the core. And that means that the core starts to contract because there's not enough energy anymore, there's not enough pressure to prevent gravity from contracting it. And so the pressure increases, temperature increases until it reaches a limit where now it can burn hydrogen to carbon and oxygen. So now you have, after this, relatively quote unquote violent phase where there were a lot of changes, now again you go through a quiescent phase where in the core you burn hydrogen to carbon and oxygen, and in the shell you burn hydrogen to helium. And so that's another phase where, just like happily burn. But at some point, even the helium is exhausted. And the sun is not massive enough to go to the next stage where you can burn carbon and oxygen. So what happens now is the core starts to contract more and more and more. And then the shell has this violent hydrogen burning, and that drives the outer layers of the star away. So what you have is what is called Planetary Nebula, and you probably have seen pictures or even taken pictures yourself of these absolutely fantastic and beautiful objects in the sky, where you have this huge nebula, and then in the core you have this carbon oxygen core, leftover core of an object like our sun. And that carbon oxygen core is basically very hot at the beginning. And if nothing happens, it just happily cools down forever and ever, and nothing will ever happen. However, sometimes, if it's not a single star, but if it was a binary or tertiary, then you can have several scenarios where you have, for example, two of these carbon-oxygen white dwarfs, this leftover cores of stars merging, and then there's enough energy to produce a supernova explosion. Another possible scenario how this carbon-oxygen white dwarf can explode is if it has a binary companion, like a red giant or a main sequence star, and they're close enough that some material from this companion star kind of like flows over to this leftover carbon-oxygen white dwarf. It slowly increases in mass, and then at some point it reaches a mass where it cannot fight against, where it then ignites and the whole carbon-oxygen core explodes. So the bottom line is, for these relatively low mass stars, what you have is they burn in the core hydrogen to helium, helium to carbon and oxygen. Then they don't have any fuel left. And if they're in a binary, then this other star, this companion star, can trigger an explosion of this carbon-oxygen white dwarf, and it just explodes and there's nothing left. And yes, and then after the explosion, of course, you can see this supernova remnant. For example, here you see Tycho's supernova remnant, which are also this beautiful nebula that you can take pictures of that are very famous. So the other cycle is when you have a very massive star, much more massive than the sun, 7, 10, even 50 times more massive. At the beginning, these stars do the same. They have hydrogen in the core, and they burn hydrogen to helium. And so that goes on. It goes on much faster than for the low mass stars, because there's so much more pressure there and so much more gravity. So at some point, it runs out of hydrogen, and then it basically goes through and burns every element to the next element. So it goes from hydrogen to helium, helium to carbon and oxygen, then from carbon to neon and magnesium, neon to oxygen, oxygen to silicon, and then at the very end, it burns silicon to iron and nickel. And that's where it stops, because you cannot have any fusion that goes further than that and releases energy. And then it has the same problem than the carbon oxygen core had. there's nothing that stops it from collapsing. And so sometimes it goes through this violent phase where there are some eruptions before it then has this gravitational collapse to a neutron star or a black hole, or it goes directly from this red supergiant, this huge blown up star, to a supernova where the whole core gravitationally collapses into a neutron star or black hole. So why are these eruptions and supernova so important? I mean, first of all, they are this really important end stage of stellar evolution. If you want to understand the stars, we also have to understand the end stage and the supernovae. There are many, many different types of supernova and eruptions. You have different composition of these stars that have an impact on how these stars explode. You have different masses, all of these different things. You have binary stars, you have single stars. And one of the most important things is that they produce and distribute the heavy elements. So everything what you see around you, everything, this carbon, oxygen, iron, your desk, your computer, this was not there at the beginning of the universe. It all got cooked in stars and then further cooked in supernovae and distributed. And then the second generation of stars that then collapsed had all of this material to form planets. The first generation of stars didn't have planets because it was hydrogen and helium and a little bit of lithium. And so we are truly made of star and supernova dust. And without supernova distributing all of this material back into the interstellar material that then collapses again and forms new stars, there wouldn't be any planets. And so when you look at the periodic system, periodic table, you can see that all of the elements all the way up to iron and around iron, they are exploding massive stars, exploding white dwarfs, which we call supernova 1As. And the higher elements are merging neutron stars. That is one of the things that we just really got to prove a few years ago. And so in the following, I will talk a lot about type 1A supernova. And that supernova are these exploding carbon oxygen cores. And then type 2 and 1B and 1C, which are all these core collapse supernova, this gravitational collapse supernova. It's beyond the scope of this talk to really talk about why astronomers have chosen such strange names for these supernovae. But I will remind you how these different supernova were, or what the characteristics are during the rest of the talk. So first I want to talk about type 1A supernovae with Kepler. And so type 1A are these supernova that you get when you have a low mass star like the sun. After it burns all of this fuel, it sheds all of the outer shells, and what's left is this carbon oxygen white dwarf. So this here is a 0th order type 1A model. You have a carbon oxygen white dwarf, so the leftover core of something like our sun. And then you have something else. And that's still the big mystery. We have different models, what can happen. 2 carbon oxygen white dwarf, or another a real main sequence or a giant companion star, but we don't know. And then you have the supernova explosion, and in this ejector of the supernova, you produce all of this nickel in the core. You have intermediate mass elements in the shell, and all of that stuff gets blown out. And we take a spectra of that looks at the energy distribution for different wavelengths. And from these spectra, we normally learn a lot about the composition, density, temperatures of the supernovae. The key is here, even though we know that it is a carbon-oxygen white dwarf that explodes, the real progenitor, what kind of companion star is it? We don't know. And that has been a big question for the last 10, 20 years, because we're also using type 1a supernova to trace the expansion of the universe. And to do this accurately, we really have to understand how they explode and what kind of systematics they could introduce at different times and redshifts. And so a lot of effort has gone into trying to understand what kind of progenitor system produces this type 1a supernova. So here is again this illustration of these two main models that might produce type 1a supernovae. So on the left side, you have these two merging white dwarfs, and as soon as they get close enough that they can actually merge, they explode. And then on the right side, you have this accretion from a companion star. So you see here this big, red giant star. You have the carbon-oxygen white dwarf right in the middle of this accretion disk. And so it's accreting and accreting and accreting material. And when it goes above a certain limit, it explodes. So these are like the two main models. There are about like 3 or 4 other models that are also suggested, that are also possible, but these are normally the two main ones. So in 2010, like 10 years ago, Dan Kaysen, a theorist at Berkeley, he came up with this idea that, hey, one way to figure out which of these progenitor channels, what kind of binary system produces 1A is to look very early in the light curve. Because if indeed we have this supernova and this main sequence or red giant, this star as a companion, when the supernova expands and has this really fast ejector and it runs into the star, then you have this huge shock. And that shock is very blue and very energetic. But it's only very short. It only lasts for days. So he did simulations. And so here you can see on the right side, the red is the supernova and the blue is a companion star, and the supernova runs into this companion star and then produces this shock. And this is directly from the paper that Dan wrote. And here is also a computer simulation from that work, and you can see that how the ejector of the supernova engulfs the star and produces this shock. I mean, you have like tens of thousands of kilometers per second ejector running into a stationary object. It's no fun. You don't want to be there, that's for sure. So what can we expect to actually see? So these here are model light curves. So on the x-axis, days since explosion. So you can see this is just like a few days after the explosion. The black line is what a normal supernova would look like. And then the different colored lines is this extra flux that gets added to this light curve when you have this shock interaction with a companion star. As you can see in the ultraviolet, that's a really strong effect. Of course, this shock is very hot and very energetic, and so it has a lot of blue light and less red light. It also, if you go back to this picture here, what you see also depends on from which angle you look at the supernova. If you look at it from the upper right, you will see a big effect. If you look at it from the lower left, you probably see much less. And that effect you can see in the right plot, where the red one is looking at this interaction face on, and the blue is looking at it from behind. So that was in 2010. And then we really we really started to look for that. We were like, okay, this is like our way to figure out if there are these, binary systems that produce type 1a supernova that have a red giant star or a main sequence star as a binary companion. And, as you see, the peak of that bump depends on the mass size and the viewing angle. And in order to see it, you need a lot of measurements right when the explosion happened. It has to be deep, it has to be high precision, and that has been the big problem of trying to find it. Because, first of all, in order to find a supernovae, you have to cover a big area of sky, so you cannot observe that normally every 1 hour or half a day or something like that. So to find a supernova that young that you can do this follow-up observation is just not easy. And so that is where the Kepler Supernovae come in, the one that Rob showed me. From these 6 supernovae that they found in their data, 3 of them were type 1a supernovae. And so here on the right side, you see the light curve of the supernova. So you see at the very beginning, there's no flux. Then at day 0, you have the explosion, and you have this rise that goes up to the peak at around 18 days after the explosion, and then it declines. And what we are interested in is these first days after the explosion. And in this inset, you see again this light curve, and then overplotted what we would expect if there would be a companion star of 2 solar masses, 6 solar masses, or a giant star. And you can see that if there would have been a companion star, we should have seen it. And in none of these 3 type 1a supernova, we found any of these this bump, this excess flux. At roughly the same time, supernova 2017 CBV blew off. And just by eye, you can already see that it has this blue, this bump that is especially pronounced in the blue. I mean, it literally was exactly what we expected from such a shock interaction. And however, and that's a bit more technical now, if you have this shock interaction with this companion star, that companion star has hydrogen and helium in the shell of the surface. So what you expect is that it sweeps up a good amount of hydrogen and helium and excites it, and that we should see the signature of this hydrogen and helium in the spectra later on. And we didn't. There was no hydrogen and no helium in the spectra. And that was really, one of the first big riddles. And, we got all ready to really start now this in more serious, in real time, get spectra in real time, all of the supernova. And then the wheels come off Kepler. One of the gyros died. And, if you want to point the telescope in space, you need 3 gyroscopes to really do this accurately. And now they had only 2 left. And so everybody thought that, okay, that's it, Kepler is done. And then they came up with an absolutely fantastic solution. I mean, there was this one engineer who had this idea, and you really have to say he's a genius. So you have 2 gyros, and then you have sun, and the sunlight has a little pressure. I mean, all those photons hitting the spacecraft gives it a little push. And this little push was enough to basically substitute the 3rd gyroscope and to allow Kepler to still take data. I mean, it was just absolutely fantastic. However, things needed to go a little bit different. Before the 2 years before, Kepler always pointed to this position for 2 years, always the same, which was nice because we got these light curves that were like, hundreds of days long. But now it could either look forward or backward so that it could use the sunlight. And so because it's moving around the sky, it could now only observe a given point of the sky for like about 80 days. So instead of like looking at one position, we had these pointings that were going all over the sky along the ecliptic. But we were back in business. We were all really excited. And as I said, to gyro mode with 80-day campaigns. And the first 15 campaigns were backward facing. And the reason was when you face forward, you have the Earth right in the field of view. And even though the Kepler is very far away, having the Earth at that, even at that distance, it's very bright. And so they didn't want to have this extra light on the detector, and so they were only backward facing. The problem was that these fields were only observable in evening twilight for about an hour. So it was very difficult to actually get ground-based data of these supernovae. And of course, you do want to have additional data of the supernova to classify them and to get extra data. But we did manage. Here's a spectra of the first supernova that we got, that Kepler observed, for which we also got a spectra. So it all worked so well, and we found supernovae, and we could get spectra, so that the Kepler mission decided to do for campaign 16 and 17 that they will face forward, and to really make this an effort, a community effort, and an extragalactic campaign. It was really awesome, and it was just absolutely, a great success. We found 32 extragalactic transients in both campaigns combined. That was more than we found in all of the other campaigns, 1 to 15 together. And it was a coordinated follow-up from many groups. I mean, we really tried to involve everyone who wanted to be involved. And then we got really lucky. The brightest supernova that we ever observed with Kepler happened during this first campaign 16, the first one that was forward facing. And so it was at a really close redshift, at a really close distance. On the right side, you have some of the discovery images. And so we were all super excited, and we thought, okay, it will be type 1a, and we will get really good upper limits on, because we really didn't think we will see a bump. We thought like, oh, we have to be really lucky to see one. And then the images got downloaded. We extracted the first preliminary data, and it was like absolutely amazing. There was this, just by eye, you could immediately see the bump in the light curve. So now the question was, okay, what is it? Is it this interaction between the supernovae with this companion star? And so now I have a couple of more technical slides for the experts. So we fit this extra bump with different models. And you can see these are 3 different models in 3 different colors. And all models fit the data really, really well. I mean, you can see the black points are the data, the observed data, and then the lines are the models, and they're actually really, really good. And the one to the right was the one that was predicted, and the 2 other ones were the ones that were, suggested after we found the first bumps in these light curves. Yes, so it's a really good fit. You can see it here on the left side. Is a fit of the data, just the bump and to the model, and you can see it's just like a really excellent fit. The color of this bump is also blue. This is something that we expect for this bump if it is this collision model. So that was in favor of the collision model, in disfavor of the other models. But like for the other supernova from the ground, when you look at the spectra, there was no hydrogen and helium. So what we would have expected is something that looks like the red line, but even bigger. And there's just nothing there. The data is just like, there was just no hydrogen and helium. So that was a little bit technical. What you have to take away from that is that right now, all of the models have issues. Could we somehow miss the swept up hydrogen and helium in the nebular phase spectra? And it's like this, it really is this ejector shock of a companion star? Or are these other models wrong and don't predict the right colors or some of the right parameters? So it is still a little bit uncertain. And that's the reason that we need more supernova with these early bumps and with more data to figure this out. So we do have more supernovae, but of course the supernova, the 1808, the one that I just talked about, is the brightest one because it was the closest one. And you can see the absolute fantastic light curve, just like a pearl of strings without any systematics. All of the other supernova that we have, they do have much less signal to noise. They are, less accurate because they are farther away and they are dimmer. But we're working on it, and we will get more limits on these things. So I just want to talk a little bit about core collapse supernovae. So core collapse supernovae are the supernova that come from very massive stars that run through all of their fuels, burn all of these different elements in their core and the shells. And at some point, there's nothing left that keeps it from collapsing because of the gravity, and you have a supernova explosion. And so these supernova, these light curves of these supernova look actually different than the type 1a supernova light curves that I just showed. You can see that they rise really fast, and then they have this plateau for sometimes 100 to 200 days before they then faint. So if you look at this really extremely fast rise, you can try to figure out some of the parameters of the progenitor star. So the red data points are from the supernova from Kepler. These are the light curves. And then the green one are models. And you can see at the left side, the model doesn't really fit the data. And when you subtract the model from the data, you have this little bump here, like very similar to this bump that we saw in type 1As. And what we think happens here is that this supernova, there was still some dusty shell around the star, and so the ejector ran into this shell, and that interaction produced again some extra energy that you can see in the light curve. Then sometimes you get also the unexpected. So we expected this core collapse supernova in type 1As, and at some point it sent another supernova light curve, and it was this one here. And at first didn't really seem like that it's so unusual, but if you look again, the rise time from explosion to peak in this case is 2 days. That's just like something we normally never see. It's an extremely fast transient. And it was so fast, it was so fast that from the ground-based data, when we monitored the Kepler field, we only had this supernova one time in one image. In the next image, 14 days later, it was already gone, and 21 days before, it hadn't exploded yet. So it was like one of the examples that we got a little bit unlucky, because if you would have detected it twice in an image, we would have detected it in real time, and then we would have gotten more data of it. But we could still analyzed it and compared to different models. And it really looks like that this supernova exploded in this dust shell. And that was the reason it was so bright and so fast. So I have one more object I want to show you, and that was also a really unusual object. We always thought that, hey, maybe we get really lucky and we get these supernova that are called type 2Bs, which are also this certain type of core collapse supernovae. And one of the reasons that we would be also interested in that and these supernova is that besides the usual supernova light curve that, you know, has a peak at around 20 days and then declines, what happens in this supernova is when the supernova explodes in the core of the star, you first don't see it because it's still inside the star. So the ejector moves outward, and at some point it breaks the surface of the star. And when it breaks the surface of the star, there's this flash, blue flash, and that then cools. And then you have the supernova light curve later on. And, you know, having one of this has been observed before, but, you know, not very well. And having such a great light curve of such an event would have been absolutely fantastic. And so we found this type 2 at, you know, not really close. And, you know, we downloaded the data and Ed looked at it and got us the first reduction. And it looked like, yeah, there's not much to that. It's, you know, pretty poor signal to noise, and we don't learn much. And, you know, a few weeks later, he came with a new reduction that was, you know, more sophisticated. And then it looked like this. And now you can see, if you squint your eye, already in the first one, you can see that there's a relatively fast first peak, and then a little bit later, something else. And if you do the real reduction, you can really see that we actually found this shock breakout and shock cooling, and then the real supernova light curve later on. And that in a way also shows you the power of Kepler. The Kepler light curve is at the bottom. And then on the other colors are the ground-based light curves. And you can see, compared to the Kepler light curve, even though we did cover some of these shock cooling of this first peak, it's just not as good as the Kepler light curve. And you can do much more with the Kepler light curve. And Patrick Armstrong, a student I worked with, he did then some model fitting, and you can see here the model are the black lines. They fit really well to the data. And with this excellent data, we can now constrain that the radius of this progenitor star was probably around 100 times bigger than the sun. And just the ejector mass, the mass that was in this ejector causing the supernova, is about 0.5 of the mass of our sun. And the velocities is about 8,000 kilometers per second. So with this data, we are then able to really, you know, constrain what kind of progenitor stars produce these different types of supernovae. So, of course, the next thing after Kepler is TESS. And of course, I don't have any time to really talk about that, but Kepler was about 100 square degrees, but it was a bigger telescope, and so it goes deeper. But TESS is absolutely fantastic because instead of like 100 square degree, it covers 2,400 square degrees in one single image. I mean, and all of the images are downloaded, not only certain cutouts. And the reason it can do that is because it has a highly elliptical orbit. So every 28 days, it gets really close to Earth, then it dumps all of the data, and then it goes away from Earth again. And that's a big difference between Kepler and TESS. So, you know, they were like, okay, how can we actually manage to get all of this data down? And yeah, so I've been working with my students and postdocs on the test data as well. We already found a lot of type 1a supernovae, other objects, core collapse, superluminous supernovae, and but that's the topic of another talk, hopefully at some point. We're still working on getting these data out. So just like to wrap up, I think I've shown you that Kepler has been an amazing facility for not only for exoplanets, but also for all kinds of extragalactic transients like supernovae and fast transients and things like that. We have found one type 1a that has this bump at the beginning, and many others don't. And I think this is really an area of a field that is developing really fast with a lot of interest of many people. We also have gotten data of core collapse supernova where we see the interactions with stellar wind and shells. And we also got lucky and found a few weird things like this fast transient and also this shock breakout and cooling of these type 2b's. Understanding all of these progenitor systems with the help of supernova helps us to understand the explosion physics and also the stellar evolution, how the different elements are cooked in stars and distributed with supernova. And now we have TESS, soon we have James Webb, and then also Roman double first. And so right now it's really exciting times, and I hope that we will find many more interesting objects. Thank you.
Thank you very much, Dr. Rest. That was a fascinating work you're doing. Thanks very much for sharing all you do with us.
Thank you.
Now I see we have a lot of questions. If you can stop sharing your slide so everybody can see us. Let me change this. Okay, so let's begin with the very basics. So your main work involves type 1a supernovae, and you also said you have detected type 2b. The question is, how many types of supernovae are there, and how frequent they are?
I think there are the two big categories are type 1a's, which are, the carbon oxygen white dwarf. It's a thermonuclear explosion. And then the other one are core collapse supernova, where you have this gravitational collapse into a neutron star or black hole that causes supernova explosion. So these are like the two main categories. But then you have a lot of subcategories in the core collapse camp. You have like, stars that only have the very cores left and no hydrogen and helium anymore. Then you have the stars that still have some helium, and you have stars that have still hydrogen and helium. And so that's kind of like another way to categorize or to subcategorize these core collapse supernovae. And then of course, you also have superluminous supernova that, that probably also are caused by a different physical mechanism. But so you have these two main categories, core collapse supernovae and the thermonuclear explosion of a carbon oxygen white dwarf.
Thank you. And the next question is, could all these types of supernovae be used to determine cosmic distances, or only certain type are more suited?
It's only certain types. It's basically only the type 1a supernovae. And one of the main reasons is that in order for a carbon oxygen white dwarf to explode, it has to go over a certain mass limit. So that means most of the times, the type 1a supernovae, when they explode, it's a similar amount of mass. And that means a similar amount of energy. That means it's kind of like the same light. And so if you have a 40 watt light bulb and you put it at different distances, just by the brightness, you can determine the relative distances. And that's what you can do with type 1As. With core collapse, it's different. All different kinds of masses and conditions. And so the brightnesses of these core collapse supernova are very different. And that's the reason you can't use them for determining the cosmic expansion.
Excellent, thank you. And we know that some supernovae can outshine a whole galaxy. Somebody wants to know, but how far does the material that they eject go compared to the size of the galaxy? Do the ejecta travel very far to the other side of the galaxy outside?
No. I mean, it depends how you define it. And I would define it that a supernova remnant is something that it can still detect. So what happens is you have the ejector, and when it travels through space and interacts with the interstellar material, you can detect these emission lines, this light that gets emitted at certain wavelengths. And when we see lots of supernova remnants, and they are still way, way, way smaller than the galaxy, and they travel with hundreds of kilometers per second, but that's not enough to really get them out of the galaxy until they fade away. So they are smaller.
Thank you. And you mentioned that you invite your collaborators from ground-based telescopes to do follow-up observations on what you do. Do you involve LIGO as well? Have they followed up any of your supernovae?
Yeah, so LIGO cannot really follow up. They run at a certain time, and they basically look at the full sky. And so I have been involved with actually with 3 different teams that do LIGO follow-up. And my software was used to detect the kilonova in 2017, from the group that was first, So that's definitely, also one of my main science areas. But that's different. You basically, whenever LIGO has a run where they have also detectors on, then you just monitor their alert system, and as soon an alert comes out, and it's a likely 2 neutron star merger, which we know can produce an optical follow-up, then you try to point the telescopes at the area that they say is the most likely area of the kilonova, and you just try to monitor it. The problem is that in the past, most of the times that area has been very big, hundreds of thousands of square degrees. And only under very good circumstances, when all 3 detectors get a signal, then you have a small area. And that was in 2017, because it was a very close by neutron star merger. And, we found it within 1 hour. I mean, it was mind blowing.
Excellent, thank you. And now the next question is, has the calculation of the Hubble constant yet been corrected for different supernovae type 1A mechanisms? Or
that is kind of one of the main reasons that we are doing what we're doing right now. So right now, I think the impact of the different progenitors is not big enough to really make a difference. However, with Roman telescope coming up, LSST, with more and more, with all of this low-Z ground-based surveys, the sample size of type 1A supernova is growing really rapidly. And so in the next 5 to 10 years, the uncertainties, the random uncertainties is getting smaller and smaller. And at that point, we will be dominated by systematics. For example, if at high redshift in early times, there was 1 channel that produced all type 1As, and it's just a teens a little bit more brighter. And now in today's time, the other channel produces most type 1A supernovae. Then you have the systematics that you don't know, and you think, oh, there's an effect. even though it's wrong. And so that's the reason we have to figure out how which progenitor system produce the different type 1As, because in the future it will be important.
Great, thank you. Now, somebody's asking about hypernovae or hypernova. Is that a type of supernova, or have there been any ones detected, or is that just a hypothetical?
I think it's one proposed channel for superluminous supernovae. You know, so the superluminous supernovae, it's still not 100% clear what produces these, you know, very, very bright supernova. And I think hypernova is one of the channels that are suggested to produce these superluminous supernovae.
Excellent, thank you. And now let's switch gears to the Kepler satellite itself. There's a couple of questions about the numbers. So do you have in mind how many total exoplanets were discovered by Kepler?
I think in Kepler it's like 5,000 or something like that, plus, you know, plus minus 1,000, I think. I think the first press release was 3,000, and then since then they have added a few thousand more.
And you, in the animation you showed, there were a lot of stars with multiple planets. So is that correct? So it discovered a lot of stars with multiple planets. Okay.
Yes. The beauty is because when a star forms, it has angular momentum, which means when it forms a disk. And the planets, of course, form in the disk. So normally all of the planets are in the same plane. So when you see one planet transiting, you probably see the other ones transiting too. And that's the reason that lots of times we, you know, if you find one planet, there's a good chance you find more than one planet.
And the next question is about data downloading of Kepler. So you mentioned you could download selected number of pixels from Kepler. Yes. Somebody wants to know, how does that work? And if you're not downloading, yeah.
So
yeah,
what happens is, so for each time period you apply that they download your favorite pixels, and that is based on your science. So you have the Exoplanet people that want to download the pixels that contain the bright stars. And then, of course, for supernova people, we don't know where the supernova goes off. So we have to monitor, you know, at least 100 galaxies to find one supernova, more like 200. And so that was really a difficult thing. So we had to, you know, compete with other programs to get pixels. And it was difficult to justify because we're like, yeah, we are fishing here, you know, and so we want to have all of these galaxies monitored, and we don't know if anything will happen there. And so that was the reason why it was difficult at the beginning to get, you know, approved and to get these pixels. As soon as we started to have success, it was much easier because it was like, yes, hey, it actually works, and we find the supernovae, and we can do something with them, and they are scientifically useful. And then they did campaign 16 and 17, where we got pretty much 95% of the pixels. And so we could really have this really big lists of, you know, I put in a list of 10,000 galaxies, and a good chunk of them was then observed and the pixels downloaded.
Okay, and am I correct in my understanding that the reason that you do selective pixels is because the transit time for the data to Earth is not long enough to get all of them, or?
Yeah, it's just so Kepler is farther away than TESS. You know, as farther away it is, it's more difficult it is to download the data. And so there's a real restriction on the bandwidth. You know, that's for all of the space telescopes is an issue. It's even an issue for JWST, where we're like, oh yeah, you know, we have to juggle a little bit around with how many images we take when, that we can download them. And so for Kepler, that was a real issue. And so that's the reason they could only download a certain amount of pixels. It was just a technical limitation.
And the next question is, if you're downloading just parts of the whole image, how do you plate solve? How do you exactly know you're looking at the same star each time you take an image?
Yeah, so the pointing of Kepler is excellent. You know, so you, in order to get this really high accuracy of the light curve, it's different than in ground-based telescope where it's moving around. So you point to a certain position and then you stay there. And the variation in your pointing is like less than a pixel. So it's really accurate. And that's the reason you can make this high accuracy measurements. So you just have to download exactly the same pixels, every single image, and you pretty much have the same object in it.
And since you mentioned about the precision of the pointing, and you mentioned you have 2 gyros only and using the sun as the third one, somebody wants more explanation on how's that done and how they could reach the level of accuracy you mentioned.
Yeah. So in K2 in the 2 gyro mode, the accuracy is not as good. You know, so the first one, you know, with 2 gyros and you could just like point, I mean, it was just like absolutely fantastic. So it wasn't as good, but they made it work. You know, I mean, I'm absolutely, you know, I was floored and impressed that this actually works. I mean, if you think about it, the pressure from the sunlight, that's not a lot. And they use it to, you know, stabilize the telescope. So yes, it's not quite as good as before, but it was definitely good enough.
And how far into the life of the Kepler mission was it for astronomer to figure out that it can be used to study supernovae?
It was 2 years, you know. So as I said, my friends, they looked for it and they just had bad luck and didn't find any in this first, like, you know, 1 or 2 years. And then Rob and Ed, they found the ones, but that was like months after the data was taken. So when Rob showed me the light curve, that was, I think, already a year after the supernova actually went off. And but that's when we said, like, okay, so now we have to get serious and you know, let's really do this. And then when we were actually ready and we were applying for time, and then it went down and K2 started, and then we had to change our strategy a little bit. Because the problem is the data gets downloaded, I think at that time it was like 3 months after it was taken. So we couldn't do real-time analysis and detection of the supernovae with Kepler data. You had to do it from the ground. That was the issue with K2, because we didn't know what we have until 3 months later, but we had to try to discover the supernova in real time, that we can take a spectra that we know the type. So that was one of the real issues at the beginning of K2 until campaign 16 and 17, when they turned the spacecraft around, and then we could observe the whole night.
Excellent. Now speaking about that KSN 2015, that anomalous. So if you only got data at minus 14 days and then the peak and then 21 days afterwards, but that plot showed many more data points. How did you determine the second day rise to the peak?
Yeah, I should have made this clear. I'm sorry. The light curve was from Kepler. And that was like the high cadence light curve. The minus 21, 0, 14, that was with Decam from the ground. That was when we were like literally in the evening twilight, you know, as soon the sun went down and they actually allowed us to point towards the fields, we were going there with a 4-wheel telescope and just took as quickly images as possible. And that was, of course, you know, difficult because you just don't have much time. And that's the reason we didn't have as much ground-based coverage. Yes, and that's the reason we didn't discover it in time to get a spectra, because then the Kepler data, the nice light curve, came 3 months later.
Okay, thank you. And okay, now next question is a little bit more diverse. So have we ever observed a core collapse supernova that became a black hole afterwards? Or that cannot be yet for sure determined?
So, yes and no. Yes, because all theory and all observations point towards that the end stage of the most massive stars that go supernova are black holes. No, because actually observing a black hole, you can't, So we know we have found the neutron stars. Of course, we have found neutron stars in our galaxies that we know must be the leftovers of the core collapse supernovae. With the black holes, it's just much more difficult to actually find them and detect them. And we cannot do them for supernova we observe because, the last galactic supernova was 500 years ago. And so the extragalactic ones in other galaxies, they're too far away to make any measurements to find the black hole that is just like a few solar masses.
Okay, thank you. And now, speaking of the galactic supernovae, are we expecting any stars nearby Earth to go supernova anytime soon?
Not really nearby Earth. The one that most likely goes off at some point in the next 10,000 years is Eta Carinae. And that's, of course, an object that is very close to my heart. I work on the light echoes of Eta Carinae's great eruption. It had its great eruption in 1840, where it basically ejected 20 solar masses. It's a 140 solar mass binary system, and it ejected 20 solar masses in these beautiful lobes. And that outburst was observed by astronomers during that time by eye, and so you can actually read how, yes, the brightness changed by, compared to this star and this star. And and so that's a prototypical, very, very massive star that at some point will explode and produce a black hole. That's literally, not much doubt that this will be a black hole.
And given that they are the most massive explosion in the universe, what's a safe distance from them? Or in other words, how far from the Earth should they be so that we're safe?
It's actually a good question, and we have thought about that. There are several things. First of all, when you have a supernova, you have the radiation, just like the light. And of course, when you are very close and it's very energetic UV light, that's not great. So direct radiation, might kill you. Of course, it also will make bad things to the atmosphere. So that's just like from the light. But then you have the ejector of the supernova. And so if the ejector reaches you and you're relatively close, then of course you have not only light bombarding you, then you have whole real, atoms hitting you with high speed. And so you also want to be at a reasonable distance. What this distance is, it's difficult to say. You have to be really close. The closest star to us is 1 light year. And if that star would explode, it probably would not be very pleasant. I think, I don't have the hard data here, so I don't want to go out on a limb. But I think normally it's, you have to have a really close star to be really severely affected. So I wouldn't worry too much.
Okay, so we're safe so far. And now the next question involves the detection of exoplanets. So for the method that Kepler uses, the transit, the inclination should be, our angle of viewing should be just right.
Yes.
But saying just right, there is some kind of the variation. It doesn't need to be exactly edge on right. It could, if it's inclined a little bit, it's fine also. So is it possible from the Kepler data to determine the inclination of the transiting planets, exoplanets orbits?
It's it's difficult because, so you have the star and then you have the planet going in front. And so if it's an inclination that gets, imagine you change the inclination. So at some point you only have a partial transit, but that looks very similar than a transit with a smaller planet. So there is a degeneracy between inclination angle, the size of the planet, and the distance of the planet to the star. So you can break some of these degeneracies with this method where you measure the wobble of the star. So that's like the first planets that were discovered were not discovered by the transit method, but they were discovered by the method where they measure the velocity of the star with spectra, and if it has this little wobble in it, and it has a certain orbital or like a certain time period, then that can be due to a planet. And so one of the big things to do is, you get the transit planets, and then afterwards you do the measurement with this other method that gives you a different parameter space, and that breaks this degeneracy a little bit, and you can take this a little bit apart. But with just the transit, you just don't know if it's just a smaller planet or if it's only a partial eclipse.
Thank you. And next question about Kepler again. Has it detected any exoplanets orbiting around black holes, binary star systems, or can it only detect exoplanets orbiting around single stars?
It has detected around binary stars. I think, it's not my field, so but I do remember there was like one discovery where it was like Tatooine from Star Wars, where they had like these two suns or something like that, so they have discovered multiple systems. I think one of the things is that if you have close binaries, it makes the orbits less stable, because you have this other really big body coming through, and it's much easier to kick out a planet out of its orbit with a big bully around than when you have a single star. So I don't know what the ratio is of binary stars and not. And I think then a long time ago, the first planets, if you want to call them, were discovered around a neutron star, and or leftover planets, because of course the neutron star went through a supernovae, and there's
so the planet was still there. That's some good news for the people who are worrying about.
I mean, that was not the full plan, and there were actually several, if I remember right. And I'm not quite sure it was like how they were detected, because it used some property of the neutron star to actually figure this out, and I forgot how it was exactly.
Okay, thank you. Now a question that is more directly related to your research. So can you tell from the spectra the extent of metallicity of the progenitor star?
You get some idea, because so the metallicity is basically, it's a really bad word that astronomers use to describe what's a fraction of the higher order elements in the star. So high metallicity means like there's a lot of carbon, oxygen, iron, and all of that extra stuff in the star. So yes, when you get the spectra, you see different lines. You see the iron lines, silicon lines, and things like that. And you normally have an idea what well, I think I'll probably take this back. I think the lines that you see in the supernova spectra are mainly produced by the elements that were produced in the supernova itself, and not so much from the star that from the progenitor star. I think it definitely has an impact on how the supernova, how the whole thing evolves, and you can get some information about that. For example, these early stars that don't have any of these higher elements, they have very different supernova explosions predicted than we see now. We have never seen this supernova from the first stars because they're so far away, and that's actually one of the things that we want to do with James Webb Space Telescope, to find these supernova from the first stars. And because there are no metals in it, no higher order element, it has a completely different way of how it burns and explodes.
Excellent, thank you. And we talked about the sizes of the ejecta of the supernova.
Mm-hmm.
And now, in terms of supernova remnants,
Mm-hmm.
What are this range of sizes in terms of light years? Do they extend more than a few light years? Okay.
I think it's a few light years at least. Yeah.
Okay.
I should know that.
And now, are there any space telescopes that are being specifically designed to study supernovae and to take their spectra?
Well, there are supernova science is a big part of the Roman Space Telescope. You know, I think there are like 3 main mission goals for Roman, and supernova, type 1a supernova science is one of them. Specifically for supernovae, I would say the Swift telescope was specifically built to, detect gamma ray bursts and now also, supernovae. But most of the big flagship missions have supernova as a component, but not as a sole goal.
Okay, there are a couple of questions only left. So about your work, you mentioned that during the interaction between the companion star and the supernova, when it interacts, when the supernova interacts with the companion star, it will excite the hydrogen or helium orbits. And then the question is, how come Kepler didn't detect any hydrogen or helium among the companion stars interacting with the supernova?
Yeah, that's really one of the big things. So with Kepler, we only get the light curve. We only get how much light is there in total. We don't get any information about hydrogen and helium specifically. However, when we take spectra, like in the late phases of the supernova, it gets transparent. So now you have the supernova, it's kind of like, going into the phase where it starts to form a supernova remnant. And so now we can see through the supernovae. So if there is now, like the carbon oxygen white dwarf didn't have any hydrogen and helium. So any hydrogen and helium must come from a companion star. So if there's a companion star with hydrogen and helium, some of that should have been swept up, and then we should have seen it in with emission lines. Because of course, when it gets swept up, you separate the protons from the electrons, and then at some point in the nebula phase, it recombines, and then you see these hydrogen and helium lines. So yes, it's absolutely mind-blowing because everything else works so well. You have this model that was predicted, we looked for it, we see the bump, and then we don't see the hydrogen and helium in the spectra. So it could be that it's actually not this companion star interaction with a supernova, but that the bump comes from some density profile in the carbon oxygen white dwarf that then, if you have this over density at the shell, you can also have this bump at the very beginning. So I don't know yet. I'm like, I did expect to see hydrogen and helium in the spectra, and we didn't see it. And I don't know why.
Great, thank you. And next question wants to know, do you think that neutrino observation from supernovae can yield details of the type of supernovae classes?
Yeah, the different supernova types will produce different amounts of neutrino, and probably also different energies of the neutrino and things like that. So when supernova 1987A exploded, they had like this really awesome detection of neutrinos. So if anything blows up in our galaxy, I think it would be with the neutrinos, that will be, I think, an absolutely mind-blowing thing to now with the current instrumentation to understand more what actually happens in supernova, because most of the energy actually gets emitted as neutrinos. And so, understanding the neutrino part of a supernova is not insignificant.
Okay, excellent. And you showed that periodic table of elements at the very beginning of your talk, and we saw a lot of elements were made in supernovae. Somebody wants to know what percentage of heavy elements are produced of slow neutron capture or not supernova, in other words?
I think the heavy elements are, the vast majority is in kilonova and the massive stars that produce supernovae. And it's only a small fraction, I think, that was in low mass stars when they're dying, when they produce planetary nebula. So most of it is in kilonova and Corker supernovae.
Okay, and another question involves against type 1 supernovae. Do all of them have the same brightness essentially, or do you use their light curve to figure out their brightness?
We have to, so they're not really, there are standard candles, which means like they have the same brightness, and there are also standardizable candles, which don't have the same brightness, but you know how it varies and you can correct for it. And type 1a supernova are the second one. So they vary by about a factor of 2.5. But as brighter they are, as slower they evolve. And so if you look at the light curve shape, you can then predict what correction you have to do to the brightness so that they all have the same brightness. And that was discovered in the 1990s by Mike Phillips, who also in Chile, so then it was used by the two teams that then discovered that the expansion of the universe is accelerating. But yeah, so that was like the first step to figure out how to correct the supernova brightness, that they are all the same, to put them basically on the same scale. And we haven't found a way to do this with any other supernovae in a similar good way. The one type of core collapse supernova, type 2p, there is a method to use the velocities that you measure in the spectra to do this correction, but it's not as good as with type 1a supernovae, and they're also fainter, so you can't go as far. So it hasn't been competitive.
Thank you. And you also mentioned, and as a lot of astronomers claim, we are made of stardust, and all the elements are produced, most of the heavy elements that we are made of are produced in supernova explosions. So somebody wants to know, so can we claim we are 100% supernova explosion, or does production of atoms and molecules some places else, maybe something happens on Earth too? So is it possible to produce somewhere else too?
It's really hard. We don't see anything. Anything that really produces large amounts of carbon, oxygen, and especially the heavier elements, it's either in stars, and that only goes basically to kind of like to iron plus minus a little bit, and everything above that, the best way is to have some really major explosion, like a supernova, kilonova, any of these events. So you always need to have one of these events that have really high temperatures and pressures to produce these heavier elements. And only, carbon and oxygen, I think you can probably also produce in, under not that extreme conditions. But it's basically stars and supernovae. I wouldn't say 100%, but close enough.
So can we say it like that the elements that we are made of was most likely produced in supernovae, but then the complex molecules we are made of was made in a cold situation on Earth?
Yeah, I mean, absolutely. Of course, the molecules you don't produce in supernova. It's way too hot. So what happens is you have the stars that produce carbon, oxygen, and then some of the heavier elements. Then supernova adds on that. It distributes it again in the interstellar material, and that cools down, and then it forms this really dense, cold clouds that then molecular clouds are actually called, where molecules form, and they then start to collapse into stars. So that's extremely cold. But to get some material there, you first had to go through a life cycle of stars and supernova explosions to get all of this material back into the interstellar medium, where it then can collapse again, cool down and collapse.
And somebody has a proposal for the reason why you're not seeing hydrogen on the binary star. And he wants to say, could it be that because the binary star, the companion star, is actually not of different age, but because the two stars form from the same nebula, there are perhaps the same level of maturity and time and lifetime. So the companion star has already had its helium or hydrogen depleted as well.
That's actually, in a way, that's like the other channel. So we have these two channels. We have the one where we have a companion star, a real star that dumps material, and then it blows up and has a shock interaction. And the other one is that you have two carbon oxygen white dwarf. And the reason you have two of them is because they were formed as, that's excellent. I mean, it really is like capturing it. Lots of the stars are formed at the same time in the same cloud, and if they have the same mass, they will evolve at the same speed and then form this carbon oxygen binary system, white dwarf binary system. And the question is actually, these systems exist. I mean, we have found them. The question is, how fast do they actually merge? And that's the issue, because if they don't merge within a Hubble time, within the age of the universe, we won't have a supernovae. And so that's a whole other fields to try to understand, how do they shed the angular momentum that they can actually come together and merge. But yes, that is literally these are like the two channels that we want to try to understand. Is it this two carbon oxygen white dwarfs, or is it a binary companion that is still a star that is not evolved?
Thank you. And as the last question, you mentioned that you work on the James Webb Space Telescope. What's the latest status? When can we expect the first light?
Well, the answer has been 1 year since 10 years, No, I mean, everything is actually looking good. And there is a small delay right now because there are issues with the Ariane spacecraft, and they had some failures, and so they had to figure out what went wrong, and so that kind of like it's like a traffic jam. So the next mission got delayed, so they have to stagger it a little bit. So I think right now it's still this fall. It's probably a few weeks later than it was originally planned, but James Webb itself, everything has checked out, all tests are passed, and I'm actually really hopeful and pretty confident actually that it will be this year.
Excellent. So thank you very much, Dr. Rest. That was a great presentation. And thank you very much for staying up this late. I understand it's past midnight where you are and answering patiently all the questions. Thank you again very much.
Thanks a lot.
So we have reached the end of this meeting. I would like to thank everybody for attending and participating and asking your questions. Please check the calendar on our website for all our upcoming events at ocastronomers.org. Thank you for joining us and have great times ahead of you. Thanks, everybody.
Thank you.